History books have lied to you about the Middle Ages. This video reveals 26 revolutionary devices that transformed medieval life, from automated surgeons to mechanical navigators, all systematically erased from our records. You will discover a hidden world of technological sophistication that forces us to rewrite everything we thought we knew about this era. Why were these marvels deliberately forgotten? And what does their suppression tell us about the fragility of knowledge itself? What forgotten invention would most surprise you to find in a medieval world? Deep within a silent monastery library, a lone monk turns a key, setting in motion a symphony of interlocking brass gears. This was the Horologum Murabile, a 12th century wonder that stands as a shocking successor to the ancient Antikythera mechanism. While we often picture the Middle Ages as a time of intellectual darkness, this device paints a radically different picture. Its intricate dials and wheels could predict the paths of planets and the precise timing of lunar eclipses decades into the future. Such a feat required a sophisticated grasp of mathematics and celestial mechanics that history books rarely grant to medieval thinkers. The very existence of this astronomical calculator shatters the myth of a scientifically stagnant era. So why does its name sound so unfamiliar today? The deliberate erasure of such a marvel forces us to question what other revolutionary ideas were lost, a mystery that only deepens with our next device. While the Horologum Murabile calculated the heavens from a quiet scriptorium, another device conquered the vast and empty oceans. Norse legends spoke of a magical stone that could capture the sun itself on the gloomiest days. This was no myth, but a sophisticated navigational tool known as a Sunstone. On the open sea, under a solid gray sky, or in the thick fog that could disorient the most seasoned sailor, a Viking navigator would hold this clear calcite crystal up to the sky. By rotating the stone and peering through it, he would watch for a subtle change deep within the gem. The crystal would polarize the scattered daylight, creating two distinct beams of light that only aligned when pointed directly toward the hidden sun. In that moment, on a featureless sea with no visible landmarks, he could pinpoint the exact location of the sun, even after it had dipped below the horizon. This gave him an unshakable reference point, a true north written in light itself. With this knowledge, Viking ships could undertake daring voyages across the North Atlantic, reaching the shores of North America centuries before Columbus. They possessed an understanding of optics and light polarization that would not be formally rediscovered until the 20th century. The existence of the Sunstone proves that medieval exploration was driven not just by courage, but by a lost science of the senses. How many other voyages of discovery were made possible by technologies we have only just begun to rediscover? This mastery over the natural world extended from the treacherous seas to the very soil beneath their feet, where another forgotten invention was quietly reshaping civilization. Yet the most spectacular demonstrations of this mechanical genius were not hidden in libraries or used for survival at sea. They were on public display, designed to inspire awe and devotion in town squares and at religious festivals. Picture a wooden stage at a medieval fair where an entire biblical play unfolds before a captivated crowd. Mechanical actors, carved from wood and painted in vibrant colors, move across the stage with a lifelike grace. A wooden angel descends from the rafters on a hidden wire, its wings flapping, a thunderous sound effect created by a lead ball rolling down a series of drums echoes through the square. All of this happens without a single human hand touching the performers. These were automated theaters, breathtaking revivals of inventions first conceived by Heron of Alexandria over 1,000 years earlier, but now refined to a stunning new level of complexity. Medieval engineers did not just copy these ancient blueprints, they improved them using intricate systems of counterweights, ropes, pulleys, and even primitive steam power to bring inanimate wood to life. Surviving manuscript fragments describe how a single, precisely weighted drive shaft could power an entire ensemble of mechanical figures for the duration of a 15-minute play. The technology behind these shows revealed a practical mastery of automation, a seamless integration of physics and artistry that would not be seen again until the automata of the Renaissance. This was entertainment, yes, but it was also a powerful statement of technological capability. So why did these marvels of public engineering vanish, leaving behind only scattered descriptions and whispers of their wonder? The answer may lie not in the fate of entertainment, but in how similar principles were applied to a far more intimate and terrifying frontier, the human body itself. The operating theater of a 13th-century hospital in Moorish Spain held a sight that would baffle a modern surgeon. There, gleaming brass automata performed delicate procedures with a steady, mechanical precision no human hand could match. Guided by intricate clockwork and detailed instructions encoded on rotating bronze discs, these machines could suture wounds with perfect, even stitches, set broken bones in ideal alignment, and carry out basic amputations with minimal tissue damage. The devices were not crude prototypes. Arabic medical texts describe how they incorporated adjustable settings for different procedures, allowing a physician to calibrate the machine's movements for a child's slender bone or a warrior's deep muscle tissue. Perhaps most astonishingly, these texts outline strict sterilization protocols. The brass arms and tools would be scoured in boiling water infused with antimicrobial herbs like thyme and sage, a practice centuries ahead of its time. This fusion of advanced mechanics and medical knowledge represented a peak of technological sophistication. Yet this entire branch of robotic surgery vanished from European medicine for hundreds of years. Its disappearance points to a catastrophic breakdown in the transfer of knowledge across cultures, a loss that becomes starkly evident when we shift our gaze from the sterile operating room to the chaotic heart of a medieval city under siege. While automated surgeons were revolutionizing medicine in the West, across the world, a different kind of machine was transforming the landscape itself. In the fertile river valleys of 11th century China, entire hillsides were carved into terraces of industry, humming with the power of flowing water. This was not a single mill, but a complex network of interconnected machines, a mechanical city powered by a single source. A central water wheel, often several stories tall, would channel its immense force through a labyrinth of wooden gears and rotating axles. These axles snaked through long workshops, each one driving a different operation. In one building, massive stone grinders pulverized grain into fine flour. Next door, the same power source operated heavy wooden hammers that pounded cloth to soften it, while in another section, trip hammers rhythmically forged metal tools. The entire complex operated as a single, coordinated organism, processing tons of material every single day with a skeleton crew of overseers. The genius of these complexes lay in their sophisticated distribution of power. Master engineers designed gear systems that could be engaged or disengaged without stopping the entire operation, allowing one workshop to be repaired while others continued production. Historical records from the Song dynasty describe automatic quality control mechanisms, like a simple cam that would eject imperfectly ground grain from the production line. They could even adjust the speed of different processes, slowing the trip hammers for delicate metalwork or speeding the grinders for coarse animal feed. This was industrial organization on a scale Europe would not achieve for another 500 years. It was a glimpse of a potential industrial revolution, fully 8 centuries before the steam engine. So what happened to this world-changing technology? The mystery of its disappearance is as profound as its creation. How could such a dominant system of production, one that promised to reshape entire economies, simply fade from global memory? The answer may lie not in the machines themselves, but in the towering structures that began to rise across the medieval world. Suddenly, the battlefield itself became a machine. While most soldiers struggled to reload a heavy crossbow in the heat of combat, a select few wielded weapons that spat death with terrifying speed. These were not ordinary crossbows. Attached to their stocks were ingenious spring-powered loading mechanisms, intricate devices of coiled animal sinew, and precisely calibrated counterweights. After each shot, the weapon would recock itself, a new bolt sliding automatically into place from a top-mounted magazine. A well-trained archer could unleash a volley of 5 bolts in the time it took a traditional crossbowman to fire just one. Obscure military manuals detail the sophistication of these systems. They featured safety locks to prevent a sudden, accidental discharge during the frantic reloading cycle. They had adjustable tension settings, allowing a soldier to prepare for a long-range siege shot or a close-quarters skirmish with a simple twist of a key. A quick-release feature could even detach the entire mechanism in an instant, converting the advanced weapon back into a standard crossbow if the complex parts jammed or broke. This was not a minor improvement. It was a revolutionary tactical advantage, a force multiplier that could decide the outcome of a battle. So why is this transformative weapon almost completely absent from our popular image of medieval warfare? Its deliberate erasure from mainstream military texts points to a pattern of organized knowledge suppression, a chilling effort to control the tools of power that becomes even more apparent with our next discovery. A plume of liquid fire erupted from the bow of a Byzantine warship, a roaring, unstoppable river of light that danced across the water and clung to enemy sails, burning even on the waves. This was Greek fire, but its true secret was not just the mysterious chemical formula, but the machine that hurled it. Mounted on the decks were complex bronze projectors, massive pumps operated by teams of soldiers. They worked a piston mechanism that compressed air in a central chamber, forcing the volatile fuel through a heated bronze tube and out a nozzle, where it was ignited to create a continuous, targeted stream. This was not a simple pot of burning oil. It was a precise pressure weapon. Recent analysis of sunken Droman ships reveals the astonishing engineering inside these projectors. They featured adjustable valves to control the flow rate, changing the stream from a tight, long-range jet to a wide, short-range spray for devastating deck-clearing attacks. The mixing chambers were lined with materials that resisted the incredible heat of the pre-ignited fuel, and the entire system was pressurized to project the fiery substance over hundreds of feet. The effectiveness of this naval flamethrower was absolute. It secured Byzantine naval dominance for centuries, turning the tide of countless sea battles and saving Constantinople from sieges on multiple occasions. And then it vanished. The knowledge of how to build and maintain these sophisticated pressure pumps was so completely lost that even the formula for the fire itself became a forgotten mystery. The disappearance was not an accident. Such a powerful weapon was a state secret of the highest order, its construction and operation likely known only to a handful of families or a single guild. Its loss points to a deliberate policy of extreme secrecy, a form of knowledge protection so absolute that it became knowledge extinction. This pattern of controlled oblivion for military advantage forces us to look for other weapons that were too effective to be widely known, technologies whose very success guaranteed their eventual erasure from the pages of history. The thunderous crash of a trebuchet stone against a castle wall was not always a matter of brute force. It was often a question of calculated precision. Master engineers did not simply build these massive machines and hope for the best. They equipped them with an array of mechanical adjustments that transformed them into the artillery of their age. The counterweight itself was not a fixed mass of stone and earth. It was often a large container, a box or sling, that could be filled with varying amounts of material. By adding or removing weight, the operator could fine-tune the force of the throw, but the adjustments went far deeper. The throwing arm's effective length could be altered, changing the leverage at the moment of release. The most critical component was the release mechanism itself. It was not a simple hook, but a sophisticated trigger that could be set to let go of the sling at different points in the arm's arc. Releasing early would send the projectile on a high, arcing trajectory to clear a high wall. A late release meant a lower, faster, and more powerful impact designed to smash straight into a fortified gate. Surviving manuscript illustrations from military engineering scrolls show detailed aiming scales etched onto the machine's frame, and accompanying tables that allowed the crew to calculate the exact settings needed for a target 400 paces away. This was applied physics on a grand scale. The complete disappearance of these adjustable systems from later medieval warfare is telling. Later trebuchets reverted to far cruder, less accurate designs. This was not a case of technological evolution. It was a clear regression, a genuine loss of sophisticated mechanical knowledge. The fate of this devastating war machine reveals how easily specialized understanding can vanish, a vulnerability that becomes even more poignant when we consider a device that sustained life rather than ending it. Beyond the clash of armies and the roar of siege engines, a quieter revolution was taking root in the earth itself. While kings and knights fought over land, a sophisticated system of articulated plows was transforming the very soil they coveted. These were not the crude, heavy boards pulled by straining oxen that we often imagine. Advanced medieval plows were marvels of modular engineering, equipped with ingenious adjustment mechanisms. A farmer could alter the depth of the cut with a simple lever, ensuring he did not tear too deeply into thin, rocky soil or too shallowly into rich, deep loam. Another control would change the angle of the moldboard, the curved surface that turns the soil over, creating a perfect furrow for either heavy wheat or delicate barley. The plowshare itself, the cutting blade at the front, could be swapped out in moments, changing from a narrow point for breaking new ground to a wide blade for weeding between rows of established crops. Farming manuals from the era read like engineering texts, detailing how these adjustments could double or even triple crop yields by creating ideal growing conditions for each type of seed. They dramatically reduced the backbreaking labor required, allowing a single farmer and his team to cultivate fields that would have previously required an entire village. The benefits were so obvious, the increase in food security so profound, that their complete disappearance from common use is one of history's greatest agricultural mysteries. This was not a technology that failed. It was a technology that succeeded and then was somehow lost. The knowledge of mechanical advantage and soil science embedded in these tools would not be rediscovered until the agricultural revolution centuries later. How could something so vital to survival simply vanish from the fields? The answer may lie not in the tools, but in the social upheavals that followed, disruptions that forced communities to look inward and develop new forms of domestic technology to survive. The clatter of a metal tray echoes through a quiet manor hall, carried not by a human servant, but by a silent figure of polished brass and carved wood. In the wealthiest homes of medieval Europe, automation had already arrived. elaborate household inventories and personal diaries describe mechanical servants powered by intricate clockwork. These automata were far more than curiosities. A wind-up butler could traverse a predetermined path on hidden tracks in the floor, delivering a decanter of wine to its master's study. Others, driven by a falling counterweight, used a system of rotating brushes to sweep the rushes on a great hall floor. The most complex among them were programmed using a pinned wooden barrel, much like a giant music box. As the barrel turned, its strategically placed pins would trip levers and gears, directing a mechanical arm through a sequence of motions. Such a device could perform the repetitive task of turning a roasting spit over the fire for hours, ensuring the meat cooked evenly without a single scullion needing to stand in the blistering heat. This was an early and remarkably effective form of domestic automation. It offered a glimpse of a future where machinery eased the burdens of daily life. The disappearance of these practical helpers is baffling. They were not weapons of war whose secrets needed guarding, nor were they dependent on rare materials. They were pure convenience, a luxury that should have become more common, not less. Their complete vanishing act suggests that the knowledge required to build and maintain them was concentrated in a few specialist workshops. When those workshops closed, perhaps due to plague or political unrest, the blueprints for a life of mechanical ease were lost with them. This strange loss of convenience technology forces us to wonder what other forms of daily comfort were sacrificed. A puzzle that deepens as we examine a device that mastered a far more elusive resource than physical labor, the very flow of information itself. A message could travel from Constantinople to Paris in a single day. While kings waited weeks for news from distant provinces, a secret network of stone towers spanning the continent flashed information across vast distances using nothing but captured sunlight. This was the optical telegraph, a system of communication so advanced it seems to belong to a different era entirely. At the summit of each tower, a massive, finely polished mirror was mounted on a complex swivel mechanism. An operator inside would receive a coded message from the previous tower in the chain, then use a series of levers and gears to tilt the great mirror, aiming a precise beam of light toward the next distant station. But this was more than a simple signal fire. The tower's windows were fitted with large, movable shutters. By opening and closing these shutters in specific, rapid sequences, the operator could send complex coded messages using the mirror's beam as a carrier. One flash might signify a specific letter, while a series of 3 quick flashes could represent an entire word, like cavalry or siege. The entire system operated on a meticulously coordinated schedule and a codebook that was a state secret of the highest order. The logistical genius required to build and maintain this network was staggering. Relay stations had to be positioned at exact intervals, always within a direct line of sight, often perched on remote hilltops or specially constructed high spires. The operators were highly trained, able to interpret and relay complex messages in minutes. Administrative fragments mention its use for everything from warning of invading armies to transmitting commodity prices between major trading centers, creating a flow of information that granted its controllers an almost prophetic advantage. For such a powerful tool to vanish completely, leaving behind only whispers in crumbling ledgers, points to something far more deliberate than mere neglect. Its erasure feels like a calculated act, a suppression of a technology that threatened to redistribute power too widely. This pattern of intentional forgetting becomes even more unsettling when we uncover a device that did not send messages, but instead recorded the most intimate human sounds. The same principles of automation that created mechanical servants were also applied to the lifeblood of civilization itself, water. In the sprawling, sun-baked cities of the medieval Islamic world, the fair and efficient distribution of water was not left to human guesswork. It was managed by brilliant brass calculating machines, intricate devices of interlocking gears that functioned as the world's first urban hydraulic computers. These were not simple clocks. They were sophisticated analog calculators designed to solve a city's most pressing problem. An engineer would input a series of variables using dials and levers, setting the machine for the current season, the estimated population in each district, and the specific water needs of nearby agricultural plots. The machine, through its precisely cut brass gears, would then compute the optimal flow rates, the necessary water pressure, and a detailed distribution schedule for the entire network of underground channels and aqueducts. It could determine, for example, that the northern orchards required a 2-hour flow at a moderate pressure on Tuesday, while the central city baths needed a continuous, high-pressure stream every afternoon. These calculations ensured that a precious resource was never wasted, maximizing crop yields and preventing conflict between neighborhoods. The complete loss of these hydraulic computers is one of history's most perplexing silences. For desert civilizations, such a device was not a luxury, it was a key to survival. Its disappearance was almost certainly not due to a lack of utility, but to the violent political fractures and wars that shattered the empires that nurtured this knowledge. When libraries were burned and engineering schools were abandoned, the blueprints for these urban lifelines turned to ash. This catastrophic fragmentation of practical knowledge forces us to look for other instruments of precision that met a similar fate, tools that measured not water, but the very fabric of reality. The 13th device transformed the night sky into a portable laboratory. For the traveling scholar of the 13th century, the universe was not locked away in a distant university tower. It was packed neatly into a custom-fitted wooden case, a complete astronomical observatory that could be carried on horseback. When opened, this case revealed a symphony of miniaturization. A folding astrolabe of engraved brass lay next to a compact armillary sphere with interlocking rings that could be assembled in moments. A sundial with a magnetic compass for leveling and a delicate sighting tube for pinpointing stars completed the set. Each instrument was designed to work in concert with the others. University ledgers from Paris and Bologna detail payments for these very devices, commissioned for masters who traveled between institutions. The true genius of these kits was their modularity. Using a set of standardized scales and conversion tables etched onto rotating discs, a scholar could take a measurement of the North Star's altitude with one instrument, then input that reading into another to calculate his precise latitude, all while standing in a windswept field. He could predict the tides for a coastal port he had never visited, or chart the position of planets for a specific date years in the future. This was not theoretical science. It was applied knowledge, a tool for navigation, timekeeping, and calendar reform that made high-level astronomy accessible anywhere on Earth. The complete disappearance of these integrated field kits points to a profound shift in how science was conducted. The scholar gradually became a stationary figure, tethered to a growing library of books rather than the portable tools of direct observation. Why would a culture abandon such a practical and empowering technology? The answer may lie in a parallel retreat from practical application in another field, one that touches the very essence of life, as our next discovery reveals a forgotten revolution in medical diagnosis. The agony of the surgeon's knife was not an unavoidable torment. In the operating theaters of major medieval medical schools, physicians possessed the means to subdue pain with scientific precision. They employed sophisticated anesthesia delivery systems, complex devices that transformed potent herbs into a controllable, breathable vapor. A typical apparatus consisted of a finely crafted ceramic burner where a specific measure of opium or mandrake root would be heated. This burner fed into an air mixture chamber where the herbal vapor was carefully blended with fresh air to achieve the correct potency. The patient would then inhale this calibrated mixture through a leather mask, often fitted with a one-way valve to ensure safe exhalation. The entire system was governed by dosage measurement. Surviving medical manuscripts describe scales and adjustable vents on the air chamber, allowing the physician to tailor the sedative strength for a large adult or a small child. Some designs even incorporated a simple water clock, a timing mechanism that would sound a soft bell when the optimal dosage had been administered, serving as a crucial safeguard against accidental overdose. For a world supposedly mired in medical darkness, this represents a stunning leap in patient care and empathy. The complete and total disappearance of these systems, despite their clear and profound benefit, is one of history's most baffling medical regressions. Why would any society willingly abandon a technology that so effectively alleviated human suffering? The answer may lie not in the failure of the devices themselves, but in the social and religious upheavals that recast such medical interventions as taboo, a cultural shift that makes the survival of our next device all the more remarkable. A silent forest of timber and canvas once turned the very wind into a form of currency. Across the plains of medieval Europe and the Middle East, towering windmills were far more than simple grain grinders. They were the beating mechanical hearts of entire industrial complexes. A single, massive windmill, with its sails catching the prevailing breeze, could power a symphony of coordinated labor through a labyrinth of interconnected gears and rotating axles that snaked out from its base. Inside a long, adjacent shed, the relentless turning of a central drive shaft operated a sawmill, where a complex crank converted the rotary motion into the back and forth movement of a blade that could slice through massive tree trunks. Further along the line, the same power source drove the heavy wooden hammers of a fulling mill, pounding raw woolen cloth to thicken and clean it. In another workshop, the relentless rhythm of trip hammers crushed ore, preparing it for smelting. The genius of these systems lay in their sophisticated power management. They did not simply run at one speed. The millers used adjustable sails, adding or removing canvas to catch more or less wind, effectively creating a mechanical throttle. They developed brilliant directional controls, often a small secondary windmill mounted on a turntable, that would automatically rotate the entire main structure to always face the wind. Contemporary technical manuscripts describe automatic shutoff mechanisms that would disengage the primary gears during storm winds, protecting the delicate wooden machinery from destroying itself. These were not just machines, they were automated factories powered by a free and renewable source of energy, operating on a scale of efficiency that would not be seen again until the Dutch Golden Age, hundreds of years later. The complete loss of this integrated approach to wind power is a profound historical puzzle. Why would a society abandon such a versatile and efficient energy system? The answer cannot be mere obsolescence, for its principles were sound. This regression becomes even more inexplicable when we discover a device that did not harness the power of nature, but instead sought to replicate the very spark of life itself. The quiet of the scriptorium was broken by the synchronized scratching of 6 pens at once. In the great monastic libraries, mechanical copiers worked tirelessly, their brass tracing arms moving in perfect unison as they duplicated sacred texts and classical works. A single monk would guide a master stylus over an original manuscript, and through an intricate system of interlocking parallelograms and gears, that exact motion was replicated by multiple writing pens on fresh sheets of vellum. These were not simple tracing toys, they were precision instruments, Library inventories from the period describe machines that could hold up to 10 pens simultaneously, each one maintaining perfect alignment and consistent ink pressure across every copy. A special clutch mechanism prevented a single pen from jamming or skipping from ruining the entire batch, isolating the fault to one copy while the others continued flawlessly. This was a revolution in information technology, dramatically accelerating the production of books while slashing the error rate that crept into every hand-copied text. For a culture on the cusp of a knowledge explosion, this device should have been priceless. Yet, on the eve of the printing press, these mechanical scribes vanished. Their abandonment is a profound historical paradox. Why discard a technology that so effectively multiplied the work of skilled scribes? The answer may lie not in the machine's failure, but in a deep-seated cultural reverence for the act of manual copying as a form of devotion and learning. The machine, for all its efficiency, removed the scribe's intimate connection to the word. This curious rejection of a labor-saving marvel finds a strange parallel in the fate of a technology that reshaped the very skyline of medieval cities, an architectural innovation that was equally brilliant and equally forgotten. High above the cobblestones, a 5-ton block of limestone drifted upward as if by magic, guided by a skeleton crew of just 3 men. This was the self-supporting architectural lifting device, a masterpiece of medieval engineering that made the impossible routine. Far from the brute force of ramps and armies of laborers, these machines transformed chaotic construction sites into models of mechanical efficiency. The core of their design was a compound pulley system of astonishing sophistication. A single rope would be threaded through multiple, independently rotating sheaves, dramatically multiplying the lifting force applied by a winch or a counterweight. Manuscripts from cathedral workshops detail systems with 8, 10, or even 12 pulleys, allowing a team of men to hoist weights that would normally require 100. But the true genius lay in the integrated braking and control mechanisms. A massive, toothed wheel known as a ratchet was mounted on the central axle. A heavy iron pawl would click against its teeth with each turn, preventing the entire load from spinning wildly backward if the workers lost their grip. This was not just a convenience, it was a lifesaver. The machines also featured precise measurement scales etched directly onto their wooden frames. These scales allowed the operator to lower a stone with millimeter accuracy, gently guiding it onto a thin bed of mortar for a perfect seal. The entire apparatus was modular. Its configuration could be adjusted for different tasks, swapping out a simple hook for a complex grappling cradle to safely lift a delicate carved statue or a fragile stained glass window. The complete disappearance of these devices from common use, even as the great cathedrals continued to rise for another 2 centuries, presents a profound historical contradiction. How could a culture forget the very tools that built its most iconic structures? This was not a gradual improvement that rendered them obsolete. It was a sudden, stark amnesia, a loss of practical knowledge so complete that later builders reverted to far more dangerous and labor-intensive methods. The vanishing of these construction marvels forces us to confront an unsettling possibility that the most fragile technology of all is not the machine itself, but the specialized, hands-on understanding required to make it work. A gleaming glass alembic sat over a gentle flame, its contents bubbling at a temperature held perfectly constant by a brass regulator. This was not magic, but the standard equipment of a medieval Arabic laboratory, a world where chemistry was already a precise and reproducible science. Technical manuscripts from the period describe entire suites of specialized glassware, from intricate distillation coils that could separate liquids by their boiling points to complex reaction vessels with multiple inlet ports for adding reagents at specific stages. The true genius of these systems lay in their control. They used standardized measurement marks etched onto the glass itself, ensuring one chemist in Baghdad could precisely replicate the experiment of another in Cordoba. Temperature was not a matter of guesswork. Ingenious thermostatic devices, often using the expansion and contraction of sealed liquids or metals, would automatically adjust the distance between a flame and the vessel, maintaining a steady heat for hours. This allowed for processes like the slow, controlled fermentation that produced pure alcohols and acids, or the precise thermal cracking that unlocked new compounds from raw materials. The chemists of this era documented their understanding of catalysts, noting how a specific mineral could dramatically speed up a reaction without being consumed, and they meticulously timed their procedures with water clocks to ensure consistency. This was a science of cause and effect, built on equipment that provided reliable data. The complete collapse of this technological tradition during Europe's Middle Ages was a catastrophe for human knowledge. It was not merely the loss of a few recipes, but the disappearance of the very tools and methods that made systematic discovery possible. Why would such a powerful and practical approach to manipulating matter simply vanish from use? The answer forces us to confront how easily the infrastructure of science can crumble, a vulnerability that becomes hauntingly clear when we examine a device that captured the most ephemeral quality of all, sound itself. The silence of an empty hall was filled by a machine composing its own symphony. In the great courts of Europe, mechanical musicians did not merely replay pre-written tunes, they generated entirely new compositions in real time. Court records describe elaborate devices powered by a central pin barrel, much like a giant music box, but this barrel was not fixed. It was a complex system of interchangeable segments, each containing a library of potential musical phrases, from a stately bass line to a lively melodic run. As the main barrel turned, it would engage a secondary mechanism, a kind of mechanical brain that selected and combined these phrases according to preset rules of harmony and rhythm encoded in its gear train. The machine could vary the tempo with a sliding weight that adjusted the speed of the drive spring, and it could even introduce algorithmic randomness by using a slowly turning wheel studded with uneven pins to make unexpected, yet musically coherent choices. The result was a limitless stream of original music, each performance unique, yet always pleasing to the aristocratic ear. This was not a player piano, it was a composer piano, a glimpse of algorithmic creativity that would not be seen again until the dawn of computer music in the 20th century. For such a marvel of entertainment and engineering to vanish completely points to a profound shift in what society valued. The very concept of machinic creativity may have become unsettling, an intrusion on the sacred realm of human genius. This erosion of a technological aesthetic finds a strange parallel in the fate of a device that mastered an even more fundamental art, the art of memory itself. The Viking longship's steering oar was not a simple plank of wood. It was the heart of a sophisticated mechanical system, a geared assembly that transformed the strength of a single helmsman into absolute command over the vessel. Archaeological finds in Scandinavian ship burials reveal the remnants of these devices, showing a complex arrangement of ropes and pulleys rigged to the massive steering oar or side rudder. This was not brute force, but a clever application of mechanical advantage. A small movement of a tiller bar by the helmsman would be amplified through the pulley system, directing the huge oak rudder through the resisting pressure of icy North Atlantic waves with surprising ease. The system even incorporated a primitive locking mechanism, a notched bar that could hold the rudder at a fixed angle. This allowed the ship to maintain a steady course for hours in a following sea, freeing the helmsman for other duties and enabling a smaller crew to manage a large vessel through the most treacherous conditions. This was naval engineering of the highest order, a technology that gave Viking explorers their legendary mastery over the sea. Its complete disappearance after the Viking Age is one of history's great nautical mysteries. Later medieval ships reverted to far more primitive steering setups, requiring multiple strong men to manage the rudder in rough weather. This was not an improvement. It was a clear and puzzling loss of knowledge, a regression that stripped sailors of a critical advantage. The quiet efficiency of this forgotten steering technology stands in stark contrast to the explosive power of our next device, a weapon that could shatter castle gates without a single touch of flame or steel. A soldier's survival could hinge on the contents of a polished wooden box. These portable field surgery kits, detailed in military medical manuals, were marvels of organized, life-saving efficiency. Far from a jumble of crude tools, each kit was a compact hospital, its interior a grid of custom-fitted compartments. One velvet-lined slot held a trephine, a precise circular saw for drilling into the skull to relieve pressure from a head wound. Another contained a specialized arrow spoon, a clever instrument designed to slide alongside an embedded arrowhead and encase its barbs, allowing a surgeon to withdraw the missile without tearing the flesh further. There were fine bone saws, their teeth set for a clean cut, and an array of needles and pre-threaded gut for suturing. But the true sophistication lay in the integrated sterilization system. A small spirit-burning stove with a foldable stand allowed a medic to boil his instruments or heat a cautery iron right on the front lines, using distilled alcohol as a clean, hot fuel. This was not haphazard first aid. It was a systematic, repeatable protocol for trauma surgery, a method that recognized infection as a killer as deadly as the initial wound. For such a logical and effective system to vanish from common use, despite the constant reality of medieval warfare, is a profound medical mystery. Why would any army abandon a technology that so clearly increased its soldiers' chances of survival? The answer cannot be a lack of need. Its disappearance points to a catastrophic breakdown in the training and logistical chains required to support such advanced field medicine, a loss that makes the quiet ingenuity of our next device all the more startling. A city's heartbeat was measured not by its crowds, but by the rhythmic chiming of a tower that was a universe in miniature. In the urban centers of medieval China, time was a public spectacle of immense sophistication. These were not simple clock towers, but multi-story engines of brass and hydraulics that dominated the main square. Powered by a constant, carefully regulated flow of water, their intricate gear trains did far more than move a single hand. One dial tracked the hours and minutes with uncanny accuracy, while another, larger face mapped the shifting positions of the planets against the fixed stars. A separate mechanical arm would point to the current phase of the lunar cycle, and a series of colored balls, released at precise intervals, indicated the state of the tides for distant coastal ports. The true marvel, however, was the automata. On the hour, tiny bronze doors would swing open. A procession of mechanical figures representing the seasons or the celestial guardians would enact a short play, their movements perfectly synchronized to the clockwork heart of the tower. An administrative edict from the Song dynasty details how these displays were calibrated to change with the agricultural calendar, showing a farmer plowing in spring and harvesting in autumn, seamlessly blending scientific observation with public education. The technology inside was just as advanced. Maintenance scrolls describe clever access panels and adjustable counterweights that allowed a keeper to fine-tune the clock's speed, compensating for changes in water pressure or seasonal temperature that might affect its accuracy. This was a communal brain, a central source of coordinated time that governed everything from market hours to religious observances. For such a comprehensive system to vanish from technological development, only to be painfully reinvented in Europe centuries later, is a staggering historical setback. Why would a society abandon a device that so perfectly organized its daily life and elevated its collective understanding of the cosmos? The answer may lie in the fragility of the specialized guilds that built and maintained these wonders, a vulnerability that becomes terrifyingly clear as we examine a device designed not for public enlightenment, but for psychological warfare. A master lens grinder could hold a piece of polished quartz up to the light and see a future where failing eyesight was no longer a sentence to helplessness. In the bustling workshops of medieval Italy and the Islamic world, the creation of eyeglasses was not a matter of chance. It was a precise science governed by specialized manufacturing devices that transformed raw crystal into perfectly curved lenses. Guild records detail mechanical grinding systems where a lens blank was mounted on a rotating spindle. Above it, a second grinding head, fitted with a specific template made of brass or hard wood, would be lowered into place. As both pieces spun, the template guided the grinder, carving an identical, perfect curve into the lens every single time. This was not handcraft, it was replication. The workshops employed standardized measurement instruments, like focal length gauges that verified the magnifying power of each finished lens. They had arrays of these brass templates, each one coded for a different strength of vision correction, from a slight aid for reading to powerful lenses for the severely nearsighted. This system allowed for the mass production of affordable vision aids, a technological democratization of sight that extended the productive lives of scholars, scribes, and artisans by decades. The demand for these glasses only grew, making their sudden technological regression all the more baffling. The precise machinery and the standardized knowledge behind it faded away, reverting eyeglass production to slow, inconsistent hand grinding for centuries. Why would a society abandon a flawless system for making a product everyone needed? The answer lies not in the lenses themselves, but in the economic structures that supported their creation, a vulnerability that becomes starkly evident in the fate of a device that managed wealth on an unimaginable scale. A single brass gear, recovered from the ruins of a forgotten Islamic observatory, contains a universe of lost mathematics. In these centers of learning, astronomy was not merely observed, it was computed with breathtaking precision by machines of polished metal and intricate design. These were not simple star charts or decorative orreries. They were true analog computers, their gear trains engineered to model the complex, looping dances of the planets with an accuracy that rivaled calculations made centuries later. A scholar would input the date using a series of calibrated dials, setting in motion a symphony of interlocking gears, including advanced epicyclic systems that perfectly replicated the apparent backward motion, or retrograde motion, of planets like Mars and Jupiter. The machine would then output the result on a finely engraved scale, revealing the planet's precise position in the zodiac, the timing of an upcoming lunar eclipse to within minutes, or the exact moment of the next equinox. Their genius was their adaptability. The devices incorporated correction mechanisms. An astronomer who noticed a slight discrepancy between the machine's prediction and what he saw in the sky could adjust a small, secondary set of gears to recalibrate the entire model, effectively teaching the machine with new observational data. This meant the devices were not static. They could evolve, incorporating new discoveries to become ever more accurate over time. The complete loss of this computational technology was a catastrophic blow to the pace of science. It forced every new generation to start from scratch, rebuilding a model of the cosmos that had already been perfected, mechanized, and then tragically forgotten. This staggering loss of a scientific tool finds its final, chilling parallel in our last discovery, a device that did not compute the heavens, but instead sought to command the very earth beneath our feet. A single flame leaping from a distant hilltop could mobilize an entire kingdom before an invading army had crossed the valley. This was the mechanical beacon network, a system of automated watchtowers that transformed light into a language of national defense. These were not simple bonfires. Each beacon was a sophisticated machine housed in a stone tower, its operation governed by clockwork precision. A massive counterweight, slowly winched upward by a keeper, was held in check by a timed release mechanism. When a signal was received from the neighboring tower, the keeper would trip the release. The falling weight would perform a series of automated tasks. It would tilt a reservoir, pouring a precise measure of flammable, resin-soaked fuel onto a prepared firebox. Simultaneously, it would strike a spark from a flint, igniting the mixture instantly into a brilliant, controlled flare. The entire sequence was shielded from the wind by a rotating cowl, a hood of polished metal that automatically turned to protect the flame from gusts that could distort the message. But the true genius was in the coding. The system used a complex language of light. A single, sustained flare might signal the approach of a small raiding party. 2 quick pulses could mean a naval invasion. 3, followed by a long burn, might indicate a siege army with heavy equipment. This allowed for detailed tactical information to race from one coast to a capital city hundreds of miles away in a matter of minutes, a speed unmatched until the electric telegraph. The disappearance of this reliable, kingdom-wide communication system is one of history's greatest military puzzles. Why would any state abandon a technology that provided such an undeniable strategic advantage? Its loss points to a final, chilling truth about the fragility of our technological heritage. The systematic erasure of these 25 devices was not a series of isolated accidents, but a pattern that reveals a profound vulnerability in human progress. This pattern of loss and forgetting culminates in our final, and perhaps most mysterious, device, one that sought not to communicate or calculate, but to command the very forces of nature. The final device was a defense against an invisible enemy. Within the thick stone walls of a besieged castle, a sentry watched a delicate silver needle quiver on a polished brass plate. This was no weather vane. It was an early warning sensor designed to detect the toxic smokes and poisonous gases that could seep through the smallest cracks, claiming entire garrisons without a single sword being drawn. Medieval defensive manuals detail entire systems dedicated to chemical warfare protection, a technology of survival that feels chillingly modern. Soldiers tasked with manning walls under a chemical cloud wore protective suits made of waxed leather or oiled cloth stitched to be airtight. Their helmets were fitted with facepieces containing a primitive but effective filter, a layered pouch of charcoal, packed herbs, and damp sponges that would scrub the air of particulate toxins before it was breathed. The air itself was the battlefield. Ventilation shafts were equipped with massive, hand-cranked fans that pushed fresh air from cleaner, higher locations into the central keep, creating positive pressure to force contaminated air out. But the true genius lay in the detection network. Strings of small, polished bells were hung in key passageways. If an invisible, heavier-than-air gas like the infamous Greek fire vapor began to pool, the cold metal of the bells would condense the vapor into visible droplets, creating a faint mist around them and silently signaling the danger. Other systems used caged birds, whose rapid respiration made them succumbing to poison long before a human would even feel a cough, serving as living alarms. This was not a scattered collection of ideas, but an integrated defensive science. It acknowledged that the greatest threat could be one you could not see, and it developed a full suite of countermeasures, from individual gear to collective air management. For such a comprehensive system of chemical defense to be perfected, only to vanish from military knowledge for centuries until the horrors of the First World War forced its desperate reinvention, is perhaps the most telling mystery of all. How could we forget how to protect ourselves? The systematic erasure of these 26 revolutionary devices forces a final, unsettling conclusion. This was not a series of unfortunate accidents. It was a pattern. The fragility of knowledge itself is the ultimate lesson. When specialized guilds dissolved, when libraries burned, when wars shattered trade routes and silenced master engineers, these technologies did not simply become obsolete. They were amputated from human understanding. Their disappearance warns us that progress is not a straight line, but a fragile thread, easily broken. Our own technological civilization, for all its data clouds and digital archives, rests on the very same precarious foundation. What have we forgotten today that some future generation will have to painfully rediscover? These brilliant minds and their creations did not vanish in a single catastrophic event. They were erased by a slow, relentless tide of historical forces, a great medieval knowledge purge that unfolded over centuries. Picture the intricate trade routes, the silk and spice roads that once pulsed with more than just goods. They carried ideas, blueprints, and skilled artisans between continents. When these networks fractured due to war or political collapse, the flow of innovation simply stopped. A master engineer in Cairo might perfect a new gear system, but without the trade routes to carry his discovery to a colleague in Constantinople, that breakthrough died with him. This isolation created pockets of genius that were incredibly vulnerable. The very secrecy that protected powerful guilds also doomed their technologies. To maintain a monopoly on their craft, guilds guarded their techniques with lethal seriousness. An apprentice learned through demonstration, not written manuals. If a guild was wiped out by plague or its members scattered by invasion, their entire library of mechanical secrets vanished in a single generation. This was not merely lost data, it was the extinction of a school of thought. The great libraries and universities, the knowledge centers of their age, became targets. The Mongol invasions systematically dismantled the irrigation computers and hydraulic networks of the Islamic world, not just conquering land but obliterating the infrastructure of the mind. In Spain, the Reconquista saw vast repositories of Arabic scientific manuscripts burned or left to rot, their contents deemed heretical. Even the peaceful monasteries, the quiet guardians of devices like the Horologum Murabile, were not safe. They were sacked and burned during regional conflicts, their scribes slaughtered and their unique manuscripts used as kindling. This was a perfect storm of fragmentation, secrecy, and violence. The result was not a gradual evolution, but a stark regression. Societies that once automated surgery and communicated with light beams found themselves struggling to reconstruct a basic watermill. This historical amnesia forces a haunting question for our own time. Our digital world, with its clouds and servers, feels permanent. But how many of our own technologies are just as fragile, dependent on a fragile chain of power grids, rare earth minerals, and specialized knowledge that exists in only a few corporate headquarters? The Great Medieval Purge warns us that no civilization, no matter how advanced, is immune to forgetting. The legacy of these 26 mysterious devices forces us to rewrite the story of the Middle Ages. This was not a dark age of superstition, but a vibrant era of invention where automated surgeons, mechanical communicators, and industrial complexes became a reality. Their systematic erasure from our collective memory represents one of history's most profound technological regressions. We are left with a vital lesson that human progress is not a straight and inevitable line forward. It is a fragile path, easily broken by the collapse of trade routes, the destruction of libraries, and the silencing of master engineers. The disappearance of these marvels is a stark warning from the past. As we now rediscover them through fragmentary manuscripts and new archaeological methods, we gain more than a corrected view of history. We gain crucial insights for our own technological future. Our modern world, with its digital clouds and global networks, may feel permanent, but it rests on the same precarious foundation of specialized knowledge and fragile infrastructure. The story of these erased devices challenges us to become better guardians of innovation, to actively preserve knowledge against the political, religious, and social forces that can still suppress revolutionary ideas. So we turn this final question to you. Of all the mysterious devices we have uncovered, from the Sunstone that guided Vikings to the mechanical beacon networks that defended kingdoms, which one do you find the most fascinating? Share your thoughts in the comments below and let us know which forgotten marvel you believe should never have been lost.